Right, this is going to be our first look at gases. As we head into this video, we're moving into chapter 5 in your textbook. I know I've promised you a number of times that when we got to this point, the material would go a bit more linearly in line with the textbook, and that should indeed be the case. In this segment, we're really just going to talk about some of the properties of gases and what they tell us and why gases are sort of interesting from a molecular perspective. Okay. Gases have several properties that are common to all gases. The first is that they have low densities compared to the other states of matter, right? There's obvious reasons for that. Partly in the same reason as gases have low densities, they're also compressible. That means we can take a gas and just change its volume quite a lot, right? It'll expand or we can compress it. You can't do that to a solid, right? If you take a solid and apply a lot of pressure to it, it generally doesn't shrink very much. You can't, if you take the pressure off, the solid doesn't re-expand. It has a volume that it wants to keep, right? Gases, in contrast, will expand to fill any container. So if I have gas in one container, if it's in a piston, say, and I raise the piston up, the gas doesn't hold the volume it used to have, right? It just moves to occupy the entire volume that's available to it. There are other things I could have put on this list. Gases mix with one another more readily than other states of matter do. Right? A gas introduced into a room will diffuse through the room relatively quickly, much more quickly than it would if we introduced a trace of something into a liquid or a solid. I included on the bottom here just one of these sort of molecular cartoon pictures of what the different states of matter might look like. This is a picture that's, gosh, it's in common with things you've seen in science textbooks going back probably at least to middle school, probably elementary school, right? That says, in the solid, our atoms or molecules are packed tightly together and they're in some nice orderly array. Right? In the liquid, they're still relatively close together, but they're now in a disordered state. They're not, tightly bound to one another. They're free to flow about, which is why a liquid doesn't have a fixed shape to it. Right? A solid generally has a shape that it holds. A liquid will flow to the shape of a container that it's in. A gas, on the other hand, has molecules or atoms that are very, very far apart from one another, right? Even that drawing there is kind of exaggerating how close together the molecules would be. In most gases, the space between two molecules is very much larger than the size of any one molecule. Okay, and that explains a lot of the properties we're talking about here, right? It's a low density because the same mass takes up more space if the atoms or molecules are that much farther apart. It's compressible because if there's that much space between molecules, if I squeeze it a bit, I can just reduce the space and the molecules won't really mind because they still have lots of room, right? So all those things, those properties that gases have in common make sense in terms of the way that the matter is actually arranged if we go down to the molecular scale. Chemists are interested in gases because gases are the phase of matter where molecules are on their own, right? In solids and liquids, the interactions between different molecules can be very important, okay? Those also can tend to be complicated and hard to figure out. So gases, each molecule is kind of just following its own trajectory, if you will, and that makes it a little bit more manageable to think about what's going to happen in gases. And that's one of the reasons why chemists like to talk about gases and why they appear fairly early in our course. So when we talk about gases, we're almost always going to do it in terms of the ideal gas law, which is written on the screen there. This is good news for you because if on the very first day of class, if I had asked everybody to write down 5 things you remembered from chemistry in high school, that equation there would probably have been on almost everyone's list, right? The ideal gas law is something that you get really used to. That equation was originally put together based on empirical observations, meaning back hundreds of years ago, people studied properties of gases and gradually put together different pieces of that and eventually built up the whole equation. It's also possible to derive that equation mathematically, starting from what is known as the kinetic theory of gases, which essentially says you take a relatively short list of assumptions about how molecules are going to behave, and then you gosh, loosely speaking, just do a physics problem involving conservation of momentum and of energy, and you can figure out that the ideal gas law has to be true based on those arguments, right? This is sort of how science works in a general kind of way. There's an empirical observation which puts together some thing that works to do predictions, but it doesn't really, no one really understands how it gets to be that way. And then somewhat later in time, people manage to do a more first principled thing and say, well, if these things are true, then that equation is true. We know the equation holds. And so that means we believe those assumptions about what the molecules are up to are therefore good descriptions of what's happening, okay? And so that's another reason to talk about this, is because it's a good mesh between sort of theory and empiricism or experimentalism to point to how we got to this point. So what is it that makes a gas act ideally? What makes a gas be an ideal gas? The sort of simplest working definition is a gas that obeys that equation is an ideal gas, is acting like an ideal gas, all right? And so we will say that that equation is going to be valid for most gases at sort of normal temperatures and pressures. And we'll talk a little bit about why that is and what that means as we go forward, okay? We want to think about molecular ideas. What would make a gas not obey the gas law, right? Because there are important circumstances where the gas law doesn't work very well, right? They most often happen, as we'll see, at conditions of very high pressures or very low temperatures. Those are the points where the gas law is most likely to fail. And we can explain those by thinking about things at the molecular level. So let's take a look at what the molecules in an ideal gas need to be doing. So here I've labeled these things as properties of an ideal gas. It's also possible to express these a little bit more formally and call them postulates of the kinetic theory of gases, which sounds a lot more impressive. But first on the list is that our ideal gas should have a very, very large number of molecules, okay? That's because a lot of the ways we put together ideas about what's going to happen are based on averages. And if you want the average to be a well-defined and well-adhered to quantity, then you want to have a lot of things, right? If you take a sample of hundreds of people on campus, what you get for the average height is probably going to be pretty close to the actual average height of people walking around on campus. If you just walk up to one or two people and get their heights, then you might get something that differs wildly from the correct average, right? So we want to have a large number of molecules. The molecules in an ideal gas, strictly speaking, are thought of as point masses, meaning the molecules themselves have no volume, all right? They're points in the mathematical sense, meaning they just don't occupy any space whatsoever. The molecules in an ideal gas exert no forces on one another. They neither attract nor repel one another, okay? So they don't, if their two molecules are cruising by, they don't push each other further apart, they don't pull each other together. Right? If their trajectories aren't going to have them meet, they don't meet. They're in constant chaotic motion. The chaotic part there refers to the gas as a whole. Each individual molecule really just is on a straight line trajectory until it hits something. And so from the molecule point of view, from a single molecule point of view, the motion's not really all that chaotic, except for the point where collisions come. But if you watch the gas as a whole, the motion is not organized in any way, right? All the molecules don't go to one side of the room and then to the other side of the room. They're just all doing their own individual things, and it all kind of works itself out. The molecules undergo elastic collisions when they collide with either each other or with the walls of the container. Okay, that's important because if that weren't true, if they lost energy every time, then the total energy of our gas would be going down as time went along, and that would mean it would be getting colder. If they gained energy, it would be getting hotter. Neither one of those things should be true. So the elastic collisions idea is important. Of those properties there, the huge number of molecules one is very easy to satisfy. Any sample of matter that's big enough that we can tell it's there is going to have a very large number of molecules, right? The two of these properties that are most suspect or most dubious, one of them that should bother us right away is this one here that says the molecules have no volume, right? If the molecules really had no volume, then if we got the thing turned into a solid, it should have no volume, right? Because the fact that the solid definitely has a volume says the molecules do take up some space, right? That assumption or that property is reasonably well obeyed as long as the space between molecules is very big compared to the size of a molecule, right? And so that's one of the assumptions that might fail. The other one that is somewhat glaringly can't really be true is the one that says there are no forces between molecules, right? If there were no forces between molecules, if molecules never attracted one another, then there wouldn't be any solids and liquids, right? Because there'd be no reason for the molecules to get stuck together if there was no interaction force between them, okay? So the fact that solids and liquids exist is pretty strong evidence that there really are some attractive forces between molecules, okay? Nevertheless, the gas law works as long as those forces are very weak compared to the energy the molecules are moving with, okay? And so that leads to the pointing out the conditions at which the gas law will fail. So the gas law will behave like an ideal gas if the pressure is low and the temperature is high. Flip that around, the gas will be less likely and will eventually not behave like an ideal gas if the pressure is high and the temperature is low, all right? If you think about it, the point where the gas law fails, high pressure or low temperature, those are the two things you might do if you wanted to turn a gas into a liquid, all right? If I had a gas and I wanted to liquefy it, I might say, I'll just raise the pressure, compress it, eventually it should liquefy, or I might say, perhaps more simply, I'll just lower the temperature, right? We cool the gas down, we know it should liquefy at some point when it gets below the boiling point. All right. In terms of the previous properties, what's happening at low pressure, the molecules are going to be further apart, right? Because as I raise the pressure, I'm forcing the molecules, I'm squeezing them closer together. So at low pressure, the assumption that the molecules are point masses is getting better and better as the pressure goes down, right? If the pressure gets very low, the molecules are further and further apart from each other, then their own volume gets more and more negligible. High temperature, what happens at high temperature is the molecules move faster, right? One definition of temperature is it's a measure of the average kinetic energy of the particles in the substance. And so at high temperature, the molecules move faster. If the molecules move faster, then those weak attractive forces between them become less important. What does that mean? If two very fast molecules cruise by one another, if there's a very small force between them, it's not really going to bend the pathway of either molecule, right? They're just going to get out of the way of each other before anything can happen. But if two very slow molecules come together and there's a force, their paths may actually bend and bring them closer together, right? So at low temperature, the assumption that the molecules don't exert forces on each other will fail, will become less valid, all right? So that's why these things hold. What does this mean? It means anytime you're about to use the ideal gas law to solve a problem, you should sort of ask yourself, does it feel okay to use the ideal gas law? Honestly, in this course, for just about every problem you do, we're going to use the ideal gas law if it's involving gases. But if you were working in an actual engineering field and you were doing a problem where you had things that were at very high pressures, hundreds of atmospheres or something like that, your ideal gas law answer probably wouldn't be very good. You still might do it that way first, just to get like the first ballpark rough estimate of what's going to happen, but you would probably then go out and get what is called a real gas equation. We'll talk a very tiny bit about those when we get towards the end of the chapter 5 material. So all this, this is what I was saying, sorry about that. The gas law is going to be okay for most gases at ordinary temperatures and pressures. Things around room temperature and pressure, just about everything that is a gas is going to obey the ideal gas law. I have to say, you can't use the ideal gas law for things that aren't gases, right? And that sounds silly, but if you've done enough gas law problems and you come upon something and it has the right sort of parameters in there, I have often seen students try to use the ideal gas law to describe things that are liquids, for example. That won't work, okay? And so just make sure that you're only using the gas law for gases. The deviations from the gas law get more severe as the pressure goes up or the temperature gets low. The low temperature part there in particular depends on what gas we're talking about, right? Because obviously different substances have different boiling points. Right? For nitrogen at room temperature, we're very far above the boiling point, and so there's no problem there. Water, obviously, is not a good ideal gas at room temperature and pressure because, well, we know it's a liquid, right? And so that tells us right away that it's not following the ideal gas law.